We are on FRQ Topic 9. We're doing polars today. Let's see. The polars. Polar questions appear pretty often. It seemed for a while they would either have a polar question or a parametrics question on it. But lately it has been on there quite a bit lately. So who knows if it'll be on this year's or not. We are going to begin our review of polars with the problem from 2018. This was number 5, no calculator. Sometimes these have a calculator and sometimes they do not. I kind of find the ones without a calculator can be easier than the ones with a calculator. That's just my personal opinion. Here we have the graphs of the polar curves. R is equal to 4, which is a circle centered at the origin. So this is the R is equal to 4. And then we have R is equal to 3 plus 2 cosine theta. That's that little limacon. They're shown on the right, and they give us our intersection points. That means, if you recall, this is what we did with that. This theta value is pi over 3. This theta value then is 5 pi over 3, which we know, if you remember when we did this, sometimes we call it 5 pi over 3, sometimes we call it negative pi over 3, depending on what our need is for that part of the problem. Okay? Part A, let R be the shaded region, and they describe the shaded region. Write an expression involving an integral for the area of R. So we don't actually have to solve the integral, we just have to write the expression. So for the area of the shaded region, here's my thought. Remember that we're going to go from theta value to theta value, and we can only go counterclockwise. So we're going to start here and go around till we get to here. So when we get to here, we are going to use this 5 pi over 3. So we're starting at pi over 3 and we're going to 5 pi over 3. We wouldn't start at pi over 3 and go to negative pi over 3. We're going to 5 pi over 3. So this will be the integral from pi over 3 to 5 pi over 3. And my outside, the outside here, is my R is equal to 4 equation. So that area will be 1/2 R squared, 1/2 of 4 squared. That's that piece of the area. And then we're going to subtract out the area of the limacon. That will give us just the shaded region. So minus 1/2 of the other R squared d theta. Recall that our area for polar is integral theta 1 to theta 2, 1/2 R squared d theta. That's our area formula. The 1/2 came from the area of a sector, a little piece of a circle. So the 1/2 is part of the area formula. We're not taking half of the area, it's part of the formula. And when you have this type of region, a combined area region, then you can always set it up like this. So that's the answer to part A. This was worth 3 points. 1 point for the constant and limits. The constant is the 1/2. The limits are the limits of integration. And 2 points for the integrand. Part B. Find the slope of the line tangent to the graph of R is equal to 3 plus 2 cosine theta at theta equals pi over 2. Slope of the line tangent is always dy dx. Always. So we have dy dx, which in polars, very similar to in parametrics, that's going to be dy d theta divided by dx d theta. We need to get x and y involved, we use the same, the two little equations, y is equal to r sine theta, x is equal to r cosine theta, where we are given the equation for r. So y is equal to 3 plus 2 cosine theta times sine theta, and x is equal to 3 plus 2 cosine theta times cosine theta. So our dy d theta will be the derivative of this. We need to use the product rule. Remember, we use the product rule consistently here. So the derivative of this piece will be negative 2 sine theta. Keep your sine theta the same. Plus, now we're leaving these parentheses alone, times the derivative of sine, which is cosine. So that's the derivative of y with respect to theta. Now for x, the derivative of this piece is still negative 2 sine theta. Leave your cosine theta alone. And then in this next piece, I'm not going to write plus yet because I remember how this worked. I'm going to leave the parentheses alone and multiply by the derivative of cosine. The derivative of cosine is negative sine. So that's our dy dx for any value. And now if we want dy dx at theta equals pi over 2, we just need to put pi over 2 in for theta. A safe stop spot here would be to replace every theta with pi over 2 and leave it like that. And that would be a safe stop spot. So if you are really unsure of your unit circle values, that's your way to do this problem. I'm very confident in my unit circle values, so I'm going to go ahead. It'll take less time for me to go ahead and put this in. Sine of pi over 2 is 1. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this would be 3 times 0 on top. On the bottom we have that negative 2 times 1 times 0 minus 3 plus 0 times 1. That would be a safe stop spot, and I'm just going to leave it there. If you change that to 2/3, that's fine too. This was also worth 3 points. 1 point for dy d theta is equal to dr d theta. This is how they wrote it. Dr d theta sine theta plus r cosine theta, or dx d theta is equal to dr d theta cosine theta minus r sine theta. So in other words, they gave 1 point if you got either the numerator here or the denominator correct. If you got either one of those correct, you got that point. 1 point was awarded for dy dx is equal to dr d theta sine theta minus r cosine theta divided by dr d theta cosine theta, that was a plus up there, minus r sine theta. So in other words, if you got the whole thing right, that was with this point. And then 1 point for the answer. Part C. A particle moves along the portion of the curve, the limacon, between 0 and pi over 2. 0 and pi over 2. So we're only looking at this part right here, between 0 and pi over 2. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. 3 units per second. Find the rate at which the angle theta changes with respect to time. What is that? That is d theta dt. The rate theta changes with respect to time, d theta dt, at the instant, so when the position of the particle corresponds to theta equals pi over 3. And we have to indicate units of measure, so hopefully I won't forget that at the end. All right, so we want d theta dt here. I know that they give me the particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. Since I know r here, the radius here from 0 to pi over 2 specifically, but really all of them, this r here is always positive. From 0 to pi over 2, r is positive. So the distance is r. The distance is r. So the distance changes at a rate of 3 units per second, tells me dr dt is equal to 3 units per second. I want d theta dt, right? I know I want d theta dt when theta is pi over 3. I know an equation that relates r and theta. So all of a sudden here, this is just a little related rates problem. Happens a lot in their last part of questions. We've done several over the course of this review. So take dt of both sides. So we'll have dr dt is equal to the derivative with respect to t. So we're doing a little chain rule. So the derivative of 3 is 0. The derivative of 2 cosine theta is negative 2 sine theta. But then we need to multiply that by d theta dt as per the chain rule. Little implicit differentiation, or the chain rule. Okay, now when theta is pi over 3, we are going to have, so dr dt is 3 sine of pi over 3, so a safe stop spot. Again, if you're unsure of your unit circle values, just write it like that. d theta dt. So d theta dt is equal to 3 divided by negative 2 sine of pi over 3. And that's a safe stop spot right there. Okay? Indicate units of measure. D theta dt. Theta is in radians. Time is in, what was time in? Seconds. Radians per second. Now, and that would be a safe stop. If you did simplify this, sine of pi over 3 is square root of 3 over 2. So the 2's cancel. We have negative 3 over square root of 3, which is the same thing as negative square root of 3. So any of those, but I would, you can totally safe stop. This was worth 3 points. 1 point for dr dt is equal to dr d theta times d theta dt. That's what we did right here. We took the derivative with respect to theta, and then we multiplied by d theta dt, little chain rule. 1 point for d theta dt is equal to dr dt times 1 over negative 2 sine theta. That was just our little piece where we solved for d theta dt, and then 1 point here for the answer with units. So they spread out those 3 points quite a bit. And that was from 2018, kind of a basic polar question. By the way, for this question back in 2018, the global average was a 4.3. That's high for any FRQ, much less a polar one. So that was high. At KHS, our kids had an average of 5.6, super high on that. So they were feeling pretty confident with their polars that year, 2018. That was our Harvey year. That was our year that we spent most of the time down at Summer Creek High School. So very impressive that they did that well on this polar Next, I would like to take a look at the problem from 2013. This was number 2. This was with a calculator. So they give us r is equal to 3. That's the circle centered at the origin. That will be this one. And then another limacon. And again, they give us the intersection point. So that's awfully nice of them. Otherwise, we would have to go find it ourselves by setting these two equal and solving for theta. So they give us this is theta equals pi over 6, and this is theta equals 5 pi over 6. Okay. Part A, let S be the shaded region and find the area of S. So area of S. So in this one, this is different from the shaded region of the first problem that we did, the one from 2018. This one, we really have two totally separate sections here. We have this section from, and remember, we can only go counterclockwise. So for this section, I'd be starting at the pi over 6 and going to the 5 pi over 6. So for that piece, I will have pi over 6 to 5 pi over 6, 1/2 that r squared. Which r are we dealing with? We're dealing with the limacon. That's the boundary of that shaded region. So 4 minus 2 sine theta squared d theta. To that integral, we're going to add the next area. For this area, let me get a different color here. We're going to start at 5 pi over 6, and we can only go counterclockwise, so we're going to go to that theta value. So if we're starting at 5 pi over 6, what should we name that theta value? Well, we go to 2 pi, and we go beyond 2 pi, pi over 6 units. So it's 2 pi plus pi over 6, or 13 pi over 6. That's one way to do it. The other way would be to go from 5 pi over 6 to 3 pi over 2 and double it, because this piece is the same as this piece. That would be another way to do that problem. If I do it this way, this will be 1/2 of that boundary's r squared. Well, that r is my 3, like that. This is with a calculator, so we grab our calculator and we are going to plug this all in. So math 9, pi over 6 to 5 pi over 6, 1/2, 4 minus 2 sine theta, close the parentheses on sine, close it on r squared d theta, plus math 9, 5 pi over 6 to 13 pi over 6, 1/2 of 9, 3 squared, d theta, and we get 24.709. That was worth 3 points that year. 1 point was for the integrand. 1 point was for the limits and constants. The constant is the 1/2. 1 point for the answer. Part B. A particle moves along the polar curve, the limacon, so that at time t, theta is t squared. Find the time in between 1 and 2 for which the x coordinate is -1. The x coordinate is -1. Well, anytime they ask me for anything involving x, I'm going to use x is equal to r cosine theta, which is 4 minus 2 sine theta cosine theta. but theta is equal to t squared. So x will be 4 minus 2 sine of t squared cosine of t squared. And I want that to be negative 1. Calculator active, so we can put in my calculator, I'm putting this in for y1, this in for y2, and I'm seeing where they intersect. Okay, so in for y1 we have 4 minus 2 sine of t squared cosine of t squared. So I'm checking, making sure it looks good, and in for y2 I'm putting a negative 1. So in for my window, I know my t's are between 1 and 2, and I just want my y's to include negative 1, so I think I'm going to go from negative 4 to 4, and that includes negative 1. There's the intersection. Let's go find it. And we get time at t is equal to 428, rounding it to 3 decimal places. This was worth 3 points. 1 point for x of theta or x of t. So if you express x, as soon as I said this x, I got that point. 1 point for x, setting x of theta equal to negative 1 or setting x of t equal to negative 1. We set x of t equal to negative 1, and then 1 point for the answer. Not bad. For the particle described in part B, find the position vector in terms of t, and then find the velocity vector at a specific time. Okay, so if we want the position vector, that's x and y, right, in terms of t. So x of t, we already wrote. X of t is right here. So I will copy that again. Y of t is our sine theta, right? So this will be 4 minus 2 sine of t squared sine of t squared. So the position vector will be a vector. It will be 4 minus sine t squared cosine of t squared, comma, 4 minus 2 sine of t squared sine of t squared. If they want a vector, I'll give them a vector, right? And then next we want to find the velocity vector at time 1.5. So the velocity vector at time 1.5 will be x prime at 1.5, y prime at 1.5. Now I just need to go ahead and find that. So x prime at 1.5, so I'm taking the derivative of x, so math 8, let's type this guy in carefully. Make sure I did that right. It looks good to me. At 1.5. So that will be that x coordinate of the velocity vector. And then for the y coordinate, I'm just sliding up, hoping that I did the x coordinate right, because I'm just going to change cosine to sine to get the y coordinate. So we will have negative 8.072, negative 1.673. and that was worth 3 points. 2 points for the position vector. 1 point for the velocity vector. And that was from 2013. Next up, we're going to take a look at the problem from 2019. This was number 2 with a calculator. I will say the problems that we just did, I feel like they were a little bit more expected, a little bit more basic for a polar question. This one you're going to see is a little bit, it has an easy part to it, but it has some more complicated parts as well. So let's let S be the region bounded by this polar curve. There's just one polar curve, there's not 2 curves going on. And they tell us what the domain is for theta. Find the area of S. Well, this is super easy. It's just the integral from 0 to pi, square root of pi, 1/2 r squared. I could even just write r, the letter r. This time, I'm going to finally wise up here, and I'm going to go ahead and put that in for my y1, just so that I can use it over and over again. So I'm using x for theta. Like that. So there's my, hopefully I got it in there right. It looks good to me. So on my home screen, Math 9, 0 to pi over, 0 to the square root of pi. Let me get there. Square root of pi of 1/2 my y1 squared. Not to the -1. Squared. 3.534. Okay, this was worth 2 points. 1 point for the integral, 1 point for the answer. All right, part B. What is the average distance from the origin to a point on the curve? What's the average distance? Well, here, from 0 to the square root of pi, r is always positive, so therefore the distance is r. The distance from the origin to a point is r. So they just want the average r, the average one of these in this. So we need to pull out of our toolbox our formula for the average value of a function, which is 1 over b minus a integral a to b of whatever you're averaging. In our case, r. That'll give it to us. So we've got 1 divided by the square root of pi. I'm making little mistakes here with my calculator. Math 9, 0 to the square root of pi of just my y1, d theta, 1.580. Rounded to 3 decimal places. That was worth 2 points. 1 point for the integral, 1 point for the answer. So if you got both of those correct, you are almost double the global average. The global average for that year was just 2.6. So if you got both of those, you're ahead of the global average. The KHS average was 3.1. So if you got both of those, you still did better than students at KHS that year. Okay? And I think that you guys can get that. No, there's nothing hard about either one of those. Let's take a look at part C. There is a line through the origin with positive slope m that divides, that should be an S here, that divides the region S into two regions with equal areas. We recall these types of questions. Write but do not solve an equation involving one or more integrals whose solution gives the value of m. So I can go up to my picture and I see what's going on here. There is a line through the origin with positive slope that divides this region into two regions of equal area. So where this region is equal to that region. This is some theta value. I don't know what the theta value is, but I know that this line has a slope of m. I need to find theta. And back when on the problems for parametric motion on our last topic review, we talked about how to get the theta value. We want that theta value. What is that theta value? Well, to get that theta value, we drop this perpendicular, and I can find the slope is m, which means rise over run is m over 1. So if I'm looking for theta, in fact, I'm going to write this all down here because AP is not going to come up here and look at your picture. So, but they will look at what you're doing down here. Okay, so there's our theta, there's our line theta, which means this angle is theta. If I drop a perpendicular, the slope here is rise over run, m over 1. So tangent of theta is m over 1, right? So theta is inverse tangent of m. Now we know what theta is. It's inverse tangent of m. So if we want we want an equation to give m, I would say, all right, 0 to arctan of m of 1/2 r squared d theta must equal the integral from arctan of m to square root of pi of 1/2 r squared d theta. And that will work. Okay? That will work. So this part was worth 3 points. 1 point for equates polar areas. So think about that. If you just wrote an equation for a polar area, you got that 1 point. That's awesome. 1 point for inverse trig function applied to m as a limit of integration. So that was definitely a tricky part, but it wasn't horrible. If we know what slope is, slope is rise over run. We learned that back in Algebra 1, right? So it wasn't just completely awful. And then 1 point for the equation. Does the equation make sense? Do your boundaries, does it all make sense? All right, part D. For k greater than 0, now we've got a k going on. For k greater than 0, let A of k be the area of the portion inside region S that is also in the circle. R is equal to k cosine theta. Remember, that's a circle on the positive x-axis of diameter k. The diameter there is k. We want to find the limit as k goes to infinity of that area. So let's think about what's going on here. When I first did this problem, I had to think about what's going on here. So I've got my original graph, my R. And now I have this circle. So the area A of K is this common interior area here. That's what that is. The diameter here is K. Now we want K to go to infinity. As K goes to infinity, what's happening? This area gets bigger and bigger and bigger, right? That area gets bigger and bigger and bigger until eventually, as K goes to infinity, this limit will be approaching the area just in the first quadrant of our original R petal. So that area, the limit as K goes to infinity of that area will be the integral from 0 to pi over 2, because we're only going to go to that first, in that first quadrant, of 1/2 r squared d theta. We actually need to find it, so we're going to go to our calculator. Integral 0 to pi over 2, 1/2 of r squared. R is still stored into my y1. 3.324. This was worth 2 points. 1 point for the limits of integration, and 1 point for the answer with the integral. So now you see why these averages were a little bit smaller. You know, was it awful? No, but this was definitely a comprehend. These both were a little bit more conceptual questions. They separated the kids who really, really knew what they were doing. All right, that's it. So polar questions don't have to take forever to do. Know your stuff, know your formulas, and know how to do these. Time for you to go try these on your own.